everyone and welcome to a new discussion which is on Darcy's law, how it is applied to the aquifers. And we have already discussed Darcy law and Reynolds numbers and flow nets, etc. But now we will move forward and how it is applied to the aquifers in the basically what I would say in real conditions also. So that our aim is to assess whatever the groundwater available to us in these geologic formations. So, for that assessment we need to know how water is moving in subsurface condition and how we can determine this movement of water, and for which we use the Darcy law as if you can recall this we have used that Q equal to K A H L upon L. So, very the same values are I am using here for that as we know that this K is transmissivity or also permeability in that sense. So, is law is used in determination of permeability. So, we can within this equation we can move a left side and right side and can determine. So, whichever the unknown quantity in this one. So, anyway lot of other inputs would be required to determine the permeability, and Darcy law when applied to an aquifer the cross sectional area A may be expressed as saturated thickness. So, we can use as word B here letter B and which times W bit width. So, this because an area is made from thickness or width or length or width. So, these two terms we are using here since this is in the vertical section. So, we are using thickness for thickness we are using B and for width W. So, the we can also write like K equal to BW. So, now K can be in the A in the Darcy law, that is equation 1 we can replace A with this BW. So, we can write like this that Q equal to K BW instead of A K HL upon L. So, this equation 3 and now we will see how we can further exploit this one. So, where we know that if we put certain values here for Darcy law, then these are the values which we can get, like hydraulic conductivity we can determine after putting these values and converting into proper units. Then what we get is that 1 meter per day hydraulic conductivity, or it can be 24.5 gallon per day per square feet, or we can also write 1.198 Darcy. Darcy is also used for units for which we say that the groundwater temperature is 20 degrees centigrade. So, by which we can determine what is the hydraulic conductivity, or if some other inputs are available to us. So, there are various types of calculators are also available in which you have to provide the values, and like from this site you can get the further details and how these calculations are done. See, one important thing in groundwater, sometimes units the given units are vary. So, as we know that all units have to be the same system, same, then only you can determine, otherwise the values whatever it will come would give a completely wrong result. So, therefore, like here that first it was the 0.1834 gallons per minute, then it was converted to millions gallons per day and then cubic feet per second. Likewise, we determine. So, here also remember 1 Darcy equal to 0.831 meter per day. So, we know that the flow, see the value is a 0.83 means roughly 83 centimeters. So, the flow of groundwater in horizontal direction is very slow compared to vertical direction, and this is just 83 centimeter, but in not all geologic formations, only in certain geologic formation this, there might be geologic formation where this flow or hydraulic conductivity might be even less than what the value is here. So, this hydraulic conductivity is most commonly expressed in this metric system, that is cubic meter per day per square meter, and this thickness and width of the aquifer we represent in meters. HL upon L also meter per meter, for HL meter, for L meter, so meter per meter, and therefore, if we write the units in Darcy law, then this becomes KBW HL upon L. So, 1 by 1, that M3 M cube per day M square multiply by M for width, for thickness, and then again HL, that L upon L. So, M upon N. So, by which if we solve this equation, simple thing, so it becomes only cubic meter per day, and this is what it is shown earlier also, that in Darcy law this is, or 1 Darcy equal to this, or hydraulic conductivity is represented per meter, meter per day likewise. So, here K is expressed depending on how the values have been given. K can be expressed in terms of gallon per day per square foot, B and W in feet, and HL in feet per foot. So, therefore, we can write like also. So, this end up with just gallon per day likewise also. So, many times we get, but in India the most common way of expressing in the metric system and cubic meter per day, that is what we, because here in 3 dimensional, so that is why cubic meter per day is coming. Now, what are the effects would be on the permeability and aquifer thickness on hydraulic gradient, because in hydraulic conductivity is also influenced by hydraulic gradient. So, therefore, and in these figures if we go one by one, these are the consider these are the equipotential lines. So, at some places these are the very close lines, as some places they are having much distance on this side also. So, there is a lot of distance is there relatively. So, what just guessing, just studying these contour lines, you see that because of the sand body here, the contour lines are very close here, and in bottom of course you are having the clay body, and these are the sandy gravels. So, relative to sandy gravels, the sand part where the contours are very close, that means the slope is relatively higher than the sandy gravels, because the hydraulic conductivity it would be very high relative to what the sand is providing. So, that would affect our hydraulic gradient. So, geologic formations, that means permeability and aquifer thickness will affect our hydraulic gradient too. So, there might be a scenario like this also, which may give us the same kind of contours, like here you are having a clay body and the rest of the things are sandy gravels. There also clay, in clay the slopes would be very high. So, that the hydraulic gradient is going to be high. So, in this map, A is a map of piezometric surface in contours and feet and the plan view of the confined aquifer. So, we are seeing from top in that one. Map B is the cross sectional, which is illustrating change in permeability, that is K, and map C, which what we are seeing is cross sectional illustrating change in thickness. So, the thickness can, if thickness changes, this is how your top figure might be same, or in case of permeability changes again. So, we have to be very careful while interpreting such maps or studying such maps. Okay. Now, these contours, these water table contours are basically, as we have seen while discussing flow nets, that these are the graphical representations of hydraulic gradient, that is HL upon L. So, if there are rivers or depending on affluent or influent rivers, these contours will vary also. So, these changes in spacing of contours, what they reflect, basically they reflect the hydraulic gradient or change in also Q, that is in discharge, hydraulic conductivity, and B for the thickness. So, aquifer thickness. So, if you are having close contours, they are it is something these three values might be influencing or will get influence from these things. So, that these close contours will represent indirectly these values like this. Similarly, the hydraulic gradient in this figure in the central part, which I was also mentioning earlier, is steeper than the side one, and that we know because of these geologic conditions, subsurface geological varying subsurface geological condition. So, here if we consider this middle figure, see these are the clay. So, that means we are having confined aquifer conditions, and we assume that no water is being added or lost in the area in confined aquifer conditions, and therefore, Q may be same throughout. But if the hydraulic gradient is different, it might affect a Q after some time. And so, the change in spacing of contour lines that we have already seen, that is the change of hydraulic gradient, and then must reflect the either a decrease in the coefficient of permeability, that is K, or a decrease in aquifer thickness, that is the central part of the area. Here the aquifer thickness is decreasing in case of this bottom example, that is the C. See the aquifer thickness has reduced here, this is only this much, whereas in other parts it is like this. So, these closed space contours are indicating various things. Now, we have to, by some means, we have to identify what is that factor, why these contours are getting close here. So, it might be affected because of hydraulic conductivity, and hydraulic conductivity affected because of different geologic organizations. So, in this again if we relook these figures, then what we found, like in figure B, that shows the Stepien gradient because of locally lower permeability which is being produced relatively compared to sandy gravels in the central part. And C shows that how gradient could be explained by thinning the aquifer. Here this gradient because of the thickness of the aquifer, the B value is changing. So, our Q will get affected. So, in many such groundwater investigations, sometimes it is possible to determine from the field data that which condition probably caused the change in gradient, because change in gradient is very important. Remember, near the well, pumping well, if gradient is high, it creates problems. Now, one of the most common, frequent and easiest way to understand that how Darcy law is used by calculating the natural flow through an aquifer. And here how observations can be made only through the bore wells which are shown here. So, X, one bore well or borehole X and borehole Y are there, and by looking the water level in these wells, we can estimate few things. So, this scenario or this schematic is a confined aquifer, which is saturated thickness in confined aquifer B is also shown, which is constant. In confined aquifer the thickness will be constant. The flow net or flow rate Q through the aquifer is from Darcy law is equal to K B W H L H upon L. So, by which by imaging a strip of aquifer with the flow occurring in the direction of bore X to Y because of the hydraulic gradient. So, this H we are determining here. So, hydraulic conductivity K, as we know, we have already discussed this part, it is meter per day. And so, in that to calculate how much water will flow in a day, the cross sectional area, that is BW, is considered. So, because it is moving, and so the B is considered and the length is considered, or the B or length, width is also considered. So, by which we know that what is the thickness of this there. So, B is there and W is there, and of course, L and HL all are there also. So, if a flow is slow, generally which is the real situation in most of the geologic formations, that flow is slow, then the kinetic energy of the water is negligible. That means movement of water, whatever the energy it is creating. So, that the hydraulic gradient can be determined from the difference in the water levels in two bore wells. So, at least when you want to drive these parameters, you need to have two water wells, so that you can get this hydraulic gradient. That is very important, as we have seen also in case of Darcy law, which is required. So, the difference in H, which is shown here, and the hydraulic gradient HL, and this simply the slope of potentiometric surface. So, here how this slope is there, by observing through bore wells or bore holes we can get, and that will go as inputs for our Darcy law. So, from Darcy law we replace these values by Q KAH upon L, here HL upon L instead, we are considering H here and L also. So, this effectiveness of rock formation, rock stratum or geologic formation, as the aquifer depends not only on its hydraulic conductivity, but on its cross sectional area. As per the Darcy law, A is important here, BW is the same thing, perpendicular to the flow direction, that is on its thickness B and width. Because in this schematic what we are seeing, that the water is flowing from X to Y direction. So, that is another important thing. So, in case of water flowing to a well, the product of hydraulic conductivity K and thickness B is important. Anyway, for determining the Q, all these parameters are important. So, this product KB means hydraulic conductivity and B for our thickness, which is generally denoted as T and which is called transmissivity. So, we are combining these two values here and calling as transmissivity. So, this Darcy law can be now written using TWH upon L. In literature you would find that various ways people have represented Darcy law, that, but remember that equation 1 here, that is the initial form of Darcy law. Then these are the replacements which are happening, like instead of KB now we are writing transmissivity, where we have written, and of course the width would be there because only B we have considered in this for transmissivity. So, width would be the thickness or the width of the aquifer, that is the cross sectional area part, and would be there, and the hydraulic gradient will also be there. So, this now units, the transmissivity have units of hydraulic conductivity multiplied by the thickness and expressed as that cubic meter per day per meter. So, by cancelling 1 m or 1 meter, it is meter square per day. So, this transmissivity is represented meter square per day. So, in some rock formations like for example, sandstones, chalk or others, the transmissivity may be in range of 1000 square meter per day. It may be very high. But in case of other types of like granitic rocks, or basaltic rock, igneous rocks or some metamorphic rocks, this transmissivity may be very less value, may have very less value. So, sometimes the hydraulic gradient that we have been considering since in equation 1 also is expressed as I, and hence Darcy law may be written as TWI. So, now we are replacing few more things, and this H upon L we can represent as I also. So, in case of now earlier examples we have taken the simple example like unconfined confined aquifer conditions. Now, we are considering the unconfined aquifers. So, there what would happen in unconfined aquifer conditions, the slope of water table is measured by the hydraulic gradient, and again you require two wells. So, bore well X and Y would be there. So, here also Darcy law can be applied, but horizontal flow occurring in only through the saturated part of the aquifer, because in confined aquifer the entire thickness is considered, but here the thickness is varying, and therefore, like in this right hand figure, now thickness we are having V1 and V2 instead of just V, because in confined aquifer conditions we can consider just one V throughout or between these two wells, but here between these two wells the saturated thickness within unconfined aquifer is varying, and therefore, different two values have to be taken to go further in and determining the either hydraulic conductivity or transmittivity or other thing. So, in such cases the transmissivity becomes the product of hydraulic conductivity K and saturated thickness B. Now, saturated thickness B is varying, so therefore, we have to consider that part also. So, in unconfined aquifers, if flow is taking place, then the water table will be sloping. In confined aquifer conditions, we did not consider that sloping water table, and due to this vertical component of flow in upper part of the saturated thickness or saturated aquifer means that a vertical hydraulic gradient must be present along with this horizontal hydraulic gradient. So, two hydraulic gradients are now considered here. It is confined aquifers are not very common. Unconfined aquifer conditions are very common, especially if I talk about India. And many times it is even in in Indo-Gangetic plain, sometimes you may find confined conditions, but in hard rock terrains generally we are getting unconfined aquifer conditions, and therefore determining all these parameters and applying Darcy law becomes further challenging. So, the vertical component has to be considered about this transmissivity. So, that can be measured by comparing water levels in the piezometers at M and N. Like here there are two wells, and so M and N, these are the piezometers have been installed. So, where we can measure and which are open only to a small thickness of the aquifer, and this will give us the vertical gradient H upon Z. And so, this here vertical has been considered. Now, horizontal hydraulic gradient can be measured by comparing water table water levels in two bore wells like B and C here, and is then H capital H upon X. That is what our becomes the horizontal hydraulic gradient. So, though two types of gradients would be considered here, and this I have this is X is there, and this on the bottom part of course you are having impermeable layer, but on top part you do not have. So, that is why it is unconfined aquifer conditions. So, now because of this vertical hydraulic gradient, the level at which the water stands in a deep bore well may not be exactly the level of water table. Why? Because if water has been withdrawn and the horizontal hydraulic gradient is not very high, then in order to attain the same water level as in the surroundings, it will take some time. So, therefore, that kind of care has to be taken while taking these values. So, if the flow is in drawdown, the head will decrease with the depth. So, the water level in a deep well will be below the water table. What is done in practice. Earlier in earlier discussion we have mentioned. So again I am repeating, any such measurements are taken in the early morning, assuming that no water has been withdrawn in the night time. So from late evening till morning, say 5 o'clock or 4 o'clock, water has not been withdrawn. I am talking about Indian conditions. So therefore, this effects of drawdown and these things would be minimum. If hydraulic conductivity is relatively good, then by the morning this will attain the same level as in the surroundings of water level. So if the flow is upward, and the head will increase with depth and the water level will stand above the water table, which is not really a common observation. Whereas layers of low permeability tend to exaggerate these vertical gradients. Of course, because if permeability is less, hydraulic conductivity is less, then the difference between water level or water table and the water level within these wells would be completely different, as you are seeing here. So, whereas in case of artesian wells, which are very rare, are examples of extreme conditions of upward flow and the water level in well standing above the ground surface. So, that means the piezometric surface is somewhere here, which is very rare, but such situations are seen. May not be exactly flowing well, but a lot of water comes. I give the example here about just south of Sivalix, you in the monsoon time, lot of such artesian conditions or flowing wells or water oozing out, coming out from surface can be seen. And so if you go near Mohand area, just south of Mohand area, in the plain part you can see such scenarios. But again in many hard rock conditions it is not. But sometimes a well can behave in if a recharge area, like if a dam is there where in monsoon time the water level has gone quite high, and in the downstream of that reservoir dam there is a say well. So what would happen, that well for some time, as long as the water is very high, water level is very high in a reservoir, that well can become an artesian well, and these things I myself have seen in the field also. But if it is remaining throughout the year, that is not very commonly seen. Anyway, so then homogeneous aquifers, again theoretical thing, no aquifer you would find homogeneous or isotropic anyway. So the relationship between T would be K and V, and is perfectly valid and straightforward. So in most of the real aquifers, as we know that this homogeneous scenario is not there. So this consists of a combination of layers of varying permeability and thickness. Because in the previous figures what we have seen that in these schematics we draw a constant thickness, but it is in natural conditions it may not be like that. So when these are the varying thickness and permeability is there, in such case the transmissivity may be determined by calculating the contribution of each layers. Its individual permeability times multiply by permeability multiply by its thickness, and adding all these contributions together. So by which we can get the average permeability of an aquifer, and that can be determined by dividing the total transmissivity of the total thickness. However, the problem becomes particularly complicated or complex in area of fissure flow aquifers, and where rather than having in normal conditions, the flow can and the groundwater flow can occur due to these fissures or fractures in the rocks, where the rock mass itself has negligible permeability and virtually all flow takes place through these few fissures, through cracks. So in a very hard rock terrain like granitic or others, if there are fractures or a kind of cracks in normal sense we say, then water only will come through these cracks or fractures. So, here the idea of this average permeability is of a limited value, and hence it vary greatly according to rock thickness over it is averaged. But in real situations we have to go for these kind of averaging of permeability, because the aquifer thickness is varying horizontally, and this hydraulic conductivity, transmissivity will also vary accordingly. So, with this we end this discussion, and thank you very much for time being. We will see you in the next discussion.